what are we at? Materials, isn't it? Sorry. Young's modulus. Okay, so let's have a look at the homework first. Yes. Why are you late? Ah, that's terrible. Come on, sit down. You got your lab report?
I'll just bring it up on the delivery.
Sit down. Alright. Let's have a look at the homework first.
This is a lot of homework, is it? And
Yes.
materials.
Yes, yes. Okay. Right. A rubber wire is hung from a table. How thick is it if it causes 100 grams? Oh, sorry. How thick is it if 100 grams cause it to extend a distance of 1 centimeter? So, what you have here? What's the rubber? Yeah. And then it extends a distance of 1 centimeter. So you know that here you have mg and here you have f. So if you wanted to, you can have f equals mg, but the f is from Hooke's law, so that's kx equals mg, and the x is 0.01 k, and the mass is 100 grams, 0.1 g. So in fact, you can get k with no trouble, firstly. (98.1 newtons). Yeah. Now, that's not quite what we want. So now we have to use the formula. Young's modulus is stress over strain. And from the table I gave you, what was the Young's modulus for rubber?
0.1 multiplied
10 power 9. And what's the formula for stress? Stress is force over area. And strain is the extension over the original length. I'll say x over L. Okay. I think we can know what the stress is, because the stress is the force over area, and I have the force here. The force F is equal to mg, so that's equal to 0.1 times 9.81, so that's equal to 0.981. Okay. And what I didn't tell you in the question, which I think I needed to tell you, is the original length of the wire. So we'll just make it 1 meter. So that means that piece there is gone. So I forgot to tell you this. Right. So we bring this up to the left. and I get 0.1 times 10 to the 9 times 0.01 equals 0.981 over the area. Okay, so we have our answer for the first question. 9.81 times 10 to the minus 7 meters squared. Got this?
Yeah.
Off the phone.
I went to WhatsApp now.
Huh?
They're in the library.
We'll go on. Okay, have you got this? Yeah. Okay, number 2. So in this one you have glass of radius 3 and has a 1 kilogram mass placed on the top of it. How much would the glass contract by? Okay. So you have some glass here. Radius is 3 and there's a 1 kilogram, I think I said 1 kilogram, did I? Yeah. Placed on the top.
Okay.
So that means there's a force downwards of mg, which equals 1g, and also there's a reaction upwards as well, if you want to think about it like that, of 1g. 9.81 newtons. 9.81 newtons. Hey, why are you late?
My printing.
Well, where's the report?
I do not know how to print.
Sit down. You had the whole week to get this ready, and you waited until this morning to print? That's right.
So the writing week.
Yeah. Right. So Young's modulus is stress over strain, which is F over A, which we know, and then the extension over the original length. Sorry, keep my letters the same. X over L. What was the Young's modulus for glass, Tekken?
70 multiplied by
70?
yeah. Yes.
Yep.
10 power
10 power 9. Okay. The force is 9.81. The area is pi 0.03 squared. The x we don't know, and the L we don't know. So if I rearrange a little bit here, I get x over L equals 9.81 over pi 0.03 squared over 7 times 10 to the 9. Okay. Oh, sorry, 7 t. So now it's telling me? So then x over L is 4.96 times 10 to the minus 8. So x is 4.96 times 10 to the minus 8 L. So I don't think I tell you the original length of the glass, do I? No. which is okay. So if I did tell you, you can work it out, but it contracts by this much multiplied by the length of the glass. So for example, e.g., if the length of the glass was, let's say some really tall piece of glass, 2 meters, for example, then the x would be a tiny number. It would be a tiny 99 nanometers. As an example. So my point I'm making here is that glass doesn't contract much. Not like rubber or something like that. Okay.
Can you zoom out?
Yes. Here?
Yeah.
Yeah. Yes. Yes. Okay. Question?
Yeah, the question.
Yes. Okay. Right. Steel wires support a lift. The lift has mass of 1500 kilograms. If the wires are 2 centimeters thick and there are 4 wires, then by how much should the wires extend by if 2 60-gram people enter the lift? Okay. Yeah. 120 kilograms, yes. Okay, so let's draw this. Okay, so there's our lift. And then we have 4 wires. And the radius of each wire is 1 centimeter. Because I said in the question they are 2 centimeters thick, so the radius is 1 centimeter. Okay. Now, what's Young's modulus for steel, please?
200 multiplied 10 power 9.
200 times
10 power
10 power 9. Yeah. Okay, so Young's modulus equals stress over strain. Now, the force here you only need to consider, I suppose I was trying to confuse you a little bit. You only need to consider the 60 grams because you imagine that the lift is already hanging. So you just want to know what happens when the 2 people step on the lift. Okay? So you don't really need to use this number. Because in the question, by how much should the wires extend by if 2 people enter the lift? So I don't want the extension from the lift and the people, just from the people. So that means we only need to consider the extra force, which is, as you said, 120 kilograms. So the force is 120 G. But because there's 4 wires, how much is in each wire then?
Divide by 4.
Yeah, divide by 4.
30.
So the force is actually 30 G only. 30 times 9.81, 294.3 newtons. Now, if we do force divided by area, we get 294.3 divided by pi, or squared, and that will equal a big number. So you get, this is the stress, 936786. Sorry, I haven't been putting in my units, they're pascals.
So one wire.
Yes. Yeah? Yeah. So we can have Young's modulus is stress over strain. That means 200 times 10 to the 9 equals 936786 over strain, which is extension over original length. So you get x over L equals 4.68 times 10 to the minus 6. So if I bring the L up here, I get the answer. So therefore, if you want to have it as a number, that is 4.68 micrometers per 1 meter of length. So for example, if you had 1 meter of steel wire, it would extend by 4.68 micrometers. If you had 2 meters of steel wire, it would extend by twice that much, because you're just multiplying by 2. If you have 3 meters, it'd be 3 times that much. So you can see that the longer the wire is, the more it would extend as well. But it's still a small amount, 4.68 micrometers is a very, very small amount. So you wouldn't even notice the change in the height of the lift when 2 people step in. And if 10 people step in, it will be 10 times this. And if we say the lift is 10 meters, would you notice it then? Let's see, times 10 times 10. Yeah, actually, if the lift is 10 meters high, and if 10 people step into the lift, maybe it's like 1/4 of a millimeter. So even in that extreme situation, you wouldn't really see the lift move much when the people step in. Okay? Alright, next one now. Sorry. Let me just favor. Okay, an unknown material is used for hanging a weight. When the weight is of mass 1 kilogram, the material extends by 1 millimeter, and when the weight is of mass 1.5 kilogram, the material extends by 2 millimeters. What is the value of Young's modulus for this material? Okay. So in the first situation, when the weight is, what did I say, 1 kilogram, that means the force is 1g, the extension is 1 millimeter, and then in the next situation, when it is 1.5, that means the force is 14.715 newtons. The extension, I think I said, is 2 millimeters. Yeah, 2 millimeters. Yeah. Yeah. Okay, so let's write down this as a formula. So you have Young's modulus is stress, which is the force over the area, divided by strain, which is the extension, which is 1 millimeter over the original length. So we can clean that up a bit. But in the second situation, so that was the first situation. In the second situation, it's also true that Young's modulus is the stress over the strain, and stress is force over area over strain, which is extension over length. So again, you get 14.715 over 0.002. Yes. Come in. Wow, why are you so late? Wait, I didn't say you could come in. Why are you so late?
There was a problem with my printer.
Uh-huh.
Yeah, he was there.
Was one extra week not enough time to have this ready?
No, this was ready.
No. There's no good answer to a question like this from your teacher. So if your teacher said, was one extra week not enough time, you don't try to defend yourself. You're supposed to go, sorry, like this. Yeah? No, sit down. Okay. Where was I? Sit. I totally forgot what I was doing now. Getting Young's modulus or something. I lost my train of thought. Yes, indeed. Okay, something went to say. So anyways, as you can see, you can't get the answer this way. Why not?
Why?
Yeah, why not?
Because we don't know technology.
Yeah, there's too many things we don't know. So I actually was picturing maybe you could do this with the graph.
Why not substitution?
There's too many unknowns. Might be better doing this way with the graph. Let's see what happens if we try to graph it. Who's WhatsApping you? Everybody's here now, aren't they?
Yeah.
Alright, do you remember what goes on the x-axis? I think it was stress, wasn't it?
Yeah.
Or no, it was strain.
Strain.
Stress. And strain was extension over length, and stress is force over area. So, do you know what? I didn't give you enough information in the question, that's why. I need to at least tell you what the area is. Anyways, what I was hoping you would do is draw the graph here. So this first point here is 1 millimeter over L, and this second point here is 2 millimeters over L, and this first point here, this lower point here was 9.81 over A, and then this upper point here was 14.715 over A. So you don't know the L and the A, but you can still kind of get an idea of what the Young's modulus is. It should be the slope. So it will be this number minus this number divided by this number minus this number. So Young's modulus should be 14.715 over A minus 9.81 over A, all over 0.001 over L minus 0.002 over L. Let's see what we get. Oh my goodness. 4.905 over A over, oh, I wrote these backwards, should be 2 here and 1 here, 0.001 over L so you get an answer of 4905 times L over A. So I need to at least give you something about the L and the A. Which I don't in the question. So this is as simple as I can make it.
Is that exam question?
Yeah, I was trying to make it like an exam question where you have to use the graph, but it is a bit of a fail. I didn't give you enough information in the question. Well, you can get this far,
Yeah.
but you don't know anything about the L over the A. So I don't know. Let's go with let's make up some numbers for the L and the A. So for example, good old 1 meter, no, let's not do 1 meter, 10 centimeters, and then the area is pi or squared. So what would be the L over A? 0.10 divided by pi times 0.01 squared, right, times 4905. So you get an answer of 1561309.99. So we'll just put 10 at the end here.
So now I think we don't need the graph.
Now you don't if you have this. 1.56 megapascals. Yeah. This was only as far as you were to get. Yes? Continue? Yeah. Okay, a boy hangs 200-gram mass at the end of a 2-meter steel wire which is attached to the ceiling. The wire is 1 millimeter thick. He pulls down on the wire slightly and releases. The mass then quickly moves up. How long until the mass reaches its maximum height? Okay. Right, so its length is 2 meters and it is 200 kilograms. So there's a 200 G force going down here, and then there's a force going up here. Right, okay. So you know Young's modulus for steel, what is it? 200 times 10 to the 9 pascals. Young's modulus is stress over strain. So that's 200 times 10 to the 9. The strain is the extension over the original length. Stress is force over area. But the force going up here, well, it's equal to this 0.200 G. Oh, and I think I tell you the thickness as well. The wire is 1 millimeter thick. So the radius is half a millimeter. Okay, so you can know that the stress is 0.200 G over pi or squared. So let's see what that number is. Two, 498,096 pascals. But you also have the formula from Hooke's law, F equals kx. So you can also know that 0.200 G is equal to K times X. Okay, and you also know that the F, yeah, oh, we wrote it there. Now, what I have to work out is the extension, which I haven't worked out, so we'll just delete that for a little bit. Okay, so I am going to continue here, but just to make some space, I'm going to go to the side for one moment. So you have your wire of length L, and then you stick your mass at the end of it. So the force down here is what did I say it was? 100 or 200 grams? 200 G. That's equal to the force, and then the force going up here is K delta Kx. But I don't tell you the K. So then that's the problem. No, when I made this question, I had an idea for a way to do this, which I can't remember now. You think? There's no way of getting the K, is there, from Young's stress over strain? That's force over area over extension over length. Rats. Rats. I don't think I told you enough again. Alright. Ah. Yeah. Terrible, absolutely terrible. Right, he pulls it down 1 centimetre. Yeah, that'll do. Huh? Plausible? I know it's steel wire, but it can be a bit flexible. So 1 centimetre. Okay, so back to, let's see. I have the stress here. So you also have F equals Kx. So now you have 2498096 equals K times 0.01. So you get K equals 2498096. No, I missed a few. 249809599. That's the K. And do you remember the formula now for the time? When you have something moving up and down like this.
Solution.
Yeah, what's the formula? It's a 2 pi square root. No, that's the pendulum. The K over M or M over K?
K over M.
Hey, double check it. Wait, are you sure? Are you sure?
And K? No, you're not sure. You found it? Okay.
So here you get 1.78 times 10 to the minus 4. But that's the time to go up and back down. You just want the time to go up to the top. So what do I need to do to this answer? That's it. 8.89 times 10 to the minus 5 seconds.
Did you get the last answer?
Divide this by 2. Yes? Okay. Right, so that's the homework then. And